This is question number 5 from June 10, SS04. It's a question on approximations. Approximations now are somewhat irrelevant because graphics calculators will contend with any parameter, but whenever values exceed those given in the AQA tables, the use of an approximation will be expected. In this question, we've got 234 guests, so we're going to need to show that we can use an approximation. It's very good before your exam to remember under exactly what conditions each distribution can be used to approximate another. In this case, we've got a very, very large n value when we come at the bottom here to summarize our distribution, and a p-value of 0.1. It's going to mean that we're going to use the normal to approximate this binomial situation. So we've got 234 guests and a probability of 0.1, and we're going to approximate that using the normal. The mean value we find by multiplying n by p to get 23.4, and the variance as it is here is n times p times q, or 1 minus p, whichever you refer to that as. So we then have a normal situation which we are using to approximate our binomial. The manager's claim was that 10% of guests come down for breakfast before 7 a.m, and that's what we're testing. It's a two-tailed 10% test. We set it up then like a z-test, and we find our z statistic by doing x minus mu over sigma. And one other point of interest here is the continuity correction. 26 guests arrived for breakfast before 7 a.m. We were actually expecting 23.4, so 26 is bigger than 23.4. So effectively we're asking, or we're looking for a probability of 26 or more in the discrete case, which equates to 25.5 or more in the continuous case. We get our z statistic of 0.457 or 0.458 to 3 significant figures, and we compare that with our critical values which we get from the tables. Remember, this was a 10% two-tailed test, so these have come from the 0.95 value from the table. The conclusion of the test in the first instance is that 0.458, our test statistic, does not lie in the critical region, and as a result we accept the null hypothesis and conclude in line with the manager's claim that there is no evidence against 10% of guests arriving at 7 a.m. Part 2 asks 2 possible reasons why the assumptions that we made in carrying out the test may not be valid. Well, we had a binomial situation here. And binomial situation, I think the first thing that we would question here is the independence of guests arriving for breakfast. If you're staying in a hotel, it's quite likely that the guests are going to arrive in family groups or in friendship groups. And the second assumption here, which I think is compromised, is that the probability will remain constant at all times. It might well be that the probability will vary at weekends or during holidays. In the second part of the question, we're asked to calculate a 95% confidence interval, which again I've done. In the question, we were given sample values, 9 sample values. Please feel free to pause this at any time. And I've come across and I've calculated the mean of those sample values and the sample standard deviation. I've then used those with a t statistic to calculate a confidence interval, getting a lower value of 58.4 and a higher value of 167. The assumption that we made in carrying out that test, which was the question for B part 2, was what assumption that we've made in order to carry that out, and that was times are assumed to be from a normal distribution. The final question asks us, go for the person who was carrying out the test was concerned that he'd made a mistake in his calculations as far fewer than 95% of the 9 values in the sample lay within the limits of the interval that he'd calculated, and we're asked to comment on his concern. Well, the confidence interval is for the population mean. Individual sample values, however, may not lie within the confidence interval at the same rate, so Gopher need not be concerned. I hope this has been a help. Please, as I've said at the start of the question, the most important thing with approximation questions is knowing when you can use each approximation for each distribution.